Dave just said, I'm going to talk from a little different perspective. He's going through from process area into materials. I'm going from materials area into process. It will be something like this. And there will be some apparent contradiction, but that doesn't mean we disagree necessarily. It just means that we have a different perspective of almost the same thing. Let's face this kind of technology. It's additive. The key is adding material, and that's the crucial one. How do we add the materials? That actually determines the kind of materials and what kind of properties we can get out of it. There's also very close coupling between process parameters and materials, and material properties we can get out. I will not go into detail into the specific material properties. If you want to have anything more that, this is something of a material selection guide that was made for Norama, a Nordic project on rapid manufacturing. It will be made available through the Custom Fit website. I think we talked about having a CD, it will be on there too, and perhaps later it will also be available on the rapid manufacturing platform. We'll try to spread that for those who are interested. Okay, that's me. I work for Sintef in Norway. For concerts out there, my accent is not Norwegian. As I said, we're talking about rapid manufacturing is additive manufacturing for end-use purposes. So that means, first, as I said, that the crucial point is adding the materials, and also that really, if the material properties are good enough for end-use purposes, it's up to you as designers and end users what kind of properties you want out. So it's quite a wide array here. It's not that easy, not that clear to determine exactly what is a rapid manufacturing, what's a rapid prototyping material. So you decide. I'll just present the options. If you take an overlook, materials can be added in different ways, like polymers up there. There are also lasers on there. Polymers up there. You can activate the addition thermally by just heating it together. And that could also be done by extrusion melting material, selective melting of the material, or you can activate the addition by chemically, either by solvent or by light exposure. Metallic materials, they can be added directly or indirectly. If it's indirectly, that is when you have made a sort of a mold by additive manufacturing and then later use that mold to cast, but then that's really costing, so I won't get into that here. The material properties will be as cast properties in that case. If you use direct adding, well, there are different phases you can use here. Gas, that's still just experimental. Liquid, micro welding, you simply melt material. Solid, that's when you fuse material in the solid phase without melting them. And then there's hybrid, when there is a little bit soft, a little bit liquid, and a little bit solid. We'll talk about that a little bit later. Ceramic, no gases. You don't melt ceramic if you usually try to avoid that. Still, but just same thing with hybrid. Could be, of course, but what practically of today is from solid materials. And then I'm going to go in and talk a little bit about FGM's functional grade materials. Polymers, these are the available material suppliers in this area. I talked about this thermal and selective thermal addition, selective melting and extrusion. FDM is basically selective extrusion, we'll go into that in a moment. Then we have SLS, David talked about that from deep, and you know it already. SMS also presented, we're going to talk briefly about that. Then chemically by light and solvent. You talk about the processes. FDM, overlook, basically what's the most common material, which Stratasys, which is the only vendor of FDM equipment in Europe and West is. There are a couple of companies in China too, but I don't think they sell anything here. Is ABS. ABS materials, that's the most. It's pretty good, it's real ABS. There's some kind of different strength when it comes to material properties independent on direction, building direction, but it's used for rapid manufacturing purposes in some occasions. Polycarbonates, a little bit stronger, a little bit different properties, can be mixed together with ABS. And then there's PPSF and PPSU that's also in the market. ABS used for medical and automotive. EMV, for example, the department of jigs and fixture are making this to make hand tools, for example. Jigs and fixture for assembly of on the car, so they are used. It's very good for them because they actually can print out with jig and fixture on location and use it directly. The tools can be a bit lighter to carry, and for the person who's making the work, if you save a couple of $100 grand, if they lift the thing a couple of 100 times a day, that actually really is a relief for them. And then polycarbonates, as I said, used to food and drugs, medical, automotive electronics, telecommunication, and so on. Selective laser sintering, the most common method for rapid manufacturing applications. Usually go into polyamide powders, that is nylons, quite often mixed with some different filler materials which have different properties, like glass powder, get more abrasion resistance, a bit stiffer. Aluminum, the same thing, but also a metallic look, better heat conduction. Flame retardant, obvious reason. Carbon, fiber, well, we can simply increase the material properties. And then there are ABS and polypropylene-like materials, thermoplastics and elastomer-like properties, polystyrene can usually used to make cast forms. Cast masters added. Here there are numerous applications. These are some examples. We have this hand tube, or I think that's called, they call it cover, that probably not the right word. And then hearing aid shells, and this is a headlight washer flap for Lamborghini cars. You can have different material properties in X-Y direction in relation to Z direction due to the orientation, the scanning orientation, how you orient the part in the build. It's worth having a look at when you try new things. Sinter mask, David talked about earlier. I could add that due to their process, they also have a more serious melting of material parts, so they claim to get a little bit better material properties than common SOS. On the other hand, they have a little bit coarser surface, so they have to be worked a little bit to afterwards. Otherwise, they have they have to have a couple of nice features. They're scoped for that process, at least I have. And selective curing by exposed laser, SLA, also talked about. It's the oldest one, most widely used, and also naturally the widest selection of materials. But since polymerization is due to exposure to light, the materials are designed to fit particular wavelengths, pulsed stuff, or solid-state laser, and other things like that. So they're not really, you can't use the same kind of resin for all kind of SLA materials. On the other hand, they're usually versions that fit each of them. The properties are in general designed to mimic conventional technical polymers. They are a little bit, don't really reach the same levels, but on the other hand, they may be quite satisfactory anyhow. And they are also mimic that ABS, nylon 6,6, polycarbonate, polypropylene, polyethylene, and so on, elastomers. You can have clear, translucent, or opaque materials. Specialty resins are also made that are use high temperature resistant film part or some nanoparticle composites and improve properties of that. And there's of course in this numerous applications apart from just visualization pieces and prototyping. You can make for automotive, of course, interior components, design components, wind tunnel testing, for short-run production, electronics parts, medical instruments, transparent products and assemblies, transparent products, like for example, for lights, different kinds there, consumer products, seal caps, key caps, and so on.